Okay, let's check sound first. Awesome. All right. So, welcome back to DX12 streams. Sorry I wasn't streaming yesterday. It's been a week and I needed a break from programming. But we're back today. Let's see. So, where we left off, we're attempting to draw a teapot and failing to draw said teapot. We wrote a lot of code last two streams, and we didn't really have a way to test that any of it was working until we were done. So today is going to be all about making this actually work. We're rendering a model and it's failing to actually draw anything. Why? So before we begin, a few things that I have done off stream. I've been continuing to expand the math library, so we have quaternions now. I had this test suite for math stuff. I have this now set up to run first thing on startup, just so that we can have some amount of regression testing for our math library while we're in the process of things. It shouldn't be too big of a problem. If it becomes, it takes 5 minutes to run all of our unit tests, then we'll put this behind a command line arg or something. But for now, we're just going to run it every time, because the more you run your tests, the more likely you'll actually find problems. Okay. So we're going to be using RenderDoc, and I figured out why RenderDoc didn't work last time, which was by default it uses this as the working directory. Well, we kind of rely on our working directory being the project folder, because we have DLLs that we have to load to get the shader compiler. And so if we're not loading, if we're not in the right working directory, then we just crash on startup because we don't load the DLL. So now that I have fixed that, we do run under RenderDoc, which is good. So you can get a frame capture, just hit an F12 and then exit out, and it'll automatically load it. So one second. So what are we looking at here? So assuming that not everyone is a graphics programmer, not everyone has had the experience of debugging in RenderDoc. We have a few things here. What RenderDoc does is it captures every API command that your renderer does for one frame. I mean, you can also have it capture several sequential frames, but pretty much it's one frame. And it determines those frame boundaries based on where your presents are. So between two presents is a frame, and that's what will get captured by a frame capture in RenderDoc. It also captures all of the resources that are used as part of this. So once you have captured a frame in RenderDoc, it can then play back command by command through your frame. And it's doing this live, like it's just literally sending the same commands down, and it can inject its own commands to do things like, hey, what happens if I clear before this draw? Does it render correctly or something, right? Which is really powerful. So that's very cool. So that's right. At a high level, that's what RenderDoc does. Is it gives you a way to step through your frame execution and figure out where things are going wrong. We also have a bunch of extra tools that are available to us here. So, for example, if I select the actual draw, there are all these overlays that we can apply. Most of which don't do anything because we're not successfully rendering, but all sorts of useful things. Like it can tell you what pixels failed depth test, what pixels are getting backface called, what pixels are outside of the stencil test, which it's all really useful information for, hey, I'm rendering something, where is it? Or, hey, some portion of this model is missing. Why is it missing? That sort of thing. It's really useful to have. So the only one of these that actually shows anything is wireframe mesh, and you'll notice that we have something that actually looks, not entirely wrong here. It's not correct, and it's not actually rendering anything, but it's not entirely wrong. So that's a positive sign. Other things we can look at. We have pipeline state, which means we can go through and examine like all of our render state for the various stages of the pipeline. So look at how our input assembler is set up. So it says that we have no input layout, no vertex buffers bound. We have an index buffer bound, and hey, here's our indices. Cool. We can look at the vertex shader, which lets us do all sorts of interesting things. Like you can actually go and look at the bytecode for the assembly. Depending on your the graphics API that you're using, you can get different results here. For example, if you are in Vulkan using SphereB for your shaders, you can actually get this to disassemble back all the way to GLSL. It's not particularly pretty GLSL, but it is, the higher level language, which is really cool. If you're on an AMD chip or you otherwise have AMD compilers installed, you can get it to actually compile to GCN and see what the actual hardware assembly is, which is really useful if you're compiling for an AMD card. NVIDIA, unfortunately, is a lot more particular about who knows about their ISA, and so all of their ISA stuff is NDA'd, and so it's not actually accessible through here. There are versions of Nsight that you can get that will actually show you assembly dumps. Those are not publicly available, and so I can't like go and get one and show you what that is. Which kind of sucks, but so this stuff is less useful for debugging per se, unless you're trying to figure out like where a 9 came from in your assembly output. But the assembly dumps are really, really useful for, hey, this fragment shader is slow, why? Because you can look and compare the instruction output you see with the shader code that you wrote and see, is the compiler doing something ridiculous? I fixed a bug at work for GCN last week, where the compiler got into its head that it could copy 4 matrices from scalar to vector registers, do a bunch of shuffles, and that would be faster than just loading another matrix from a buffer. So you can learn a lot about the decisions the compiler makes and how to convince the compiler otherwise by actually looking at the final assembly. However, that's not really useful for what we're doing today, because I'm pretty sure that our shaders are simple enough that they are doing what they're supposed to. The other thing useful in the shader tabs is we have access to all of the bound resources, which is fantastic. So let's go look at our structured buffer, which contains our vertex data. If we open it up, right now it just gives us a list of bytes. Well, bytes are not particularly useful. But down here, we can tell RenderDoc what format it should use here. Like we can tell it what this data actually looks like in practice. So we have float3 position, a float3 normal, and a float2 text chord, but we don't actually fill in text chord ever. So now if I go down here and hit apply, it formats everything. So we can scan through this list, and this looks reasonable. You may notice that we have the same normal for every vertex. That is because the OBGA that we loaded does not have vertex normals in it. So fast OBGA is just giving us a dummy normal to pack in. Once we get things rendering, we will be able to go in and compute proper vertex normals. I'm not going to bother with that right now because I want to get the thing rendering on screen before I consider how to make it render correctly. So this is actually a really good sign because it means that our buffer bindings are very likely correct. So at the end of last stream, I was concerned that maybe I had messed up the root signature, and that was why we weren't getting anything rendering. It looks like that's not the case because, if RenderDoc can resolve our bindings, then the GPU can, usually. The other binding we have is our constant buffer, which we can go look at. Again, it decides that these are uint4s. I don't know why, but we can do the same thing where we say, no, actually, these are float4s. Y, and there's our matrix. Now, here is our first actual problem. And full disclosure, I realized this between streams. So I didn't just see this and immediately discover that this was the problem, but this is not the only problem. So what's happening here is these two values are swapped from where they should be. So this is our near plane, and right now we okay, let's step back for a second. So in order for a projection matrix to work, we kind of have to, like, one of those structural things about projection matrices is that they want you to be dividing x and y by z. That's what gives you the perspective, like the angled frustum, because x and y increases as z increases and so on. Like the range of x and y that gets mapped to 0 to 1 increases as z increases, right? So for that to happen, our w in the output needs to depend on, or it needs to be basically our z value. So each of these rows is, so this produces the x coordinate of our output, the y coordinate of our output, the z coordinate of our output, and the w coordinate of our output. And these row vectors get dotted with the position vector. Now, because we have the near plane here, we're scaling z when we put it into w. That's actually not correct. So that's a problem. What we want is for a -1 to be here and the near plane to be here. Because then, like, when we do the post-projected divide, so when we divide the result by w, we want the z after division to be near plane over -z, because we have a reversed depth buffer and so on. So we need near plane to be up here so that it goes unmodified into z, and then we need z -1 to be here because that will give us -z in w, which will then divide everything out correctly. Okay, so long-winded explanation, but hopefully it made some amount of sense. So let's go ahead and fix that. Over in our matrix functions, So we need to take these two and swap them. We need to do the same for the inverse, otherwise our unit tests will complain. Even though we aren't using this for anything in our rendering yet. So, as I said, full disclosure, I've done this before. I know that this will not actually fix the problem, but it'll get us a step towards fixing the problem. Because this is a bug, whether or not it's the only bug. So we've made a change to shaders. So now we're actually going to have to launch again and get a new capture. We need the new shaders. Capture again. So now our matrix looks correct. We scale our X values a bit more than we scale our Y values because our screen is wider than it is tall. Seems reasonable. And actually, does that seem reasonable? Maybe this is actually backwards. I don't know. I don't think it would completely break everything if it was, though. So this matrix looks reasonable, but obviously we're still not rendering anything. However, if we look at the wireframe mesh now, like this looks pretty close to what you would expect, you know, rendered mesh to look like, right? But none of this is getting backface called, none of it's getting depth tested because we don't even have a depth buffer. So most likely what is happening is the mesh is behind the camera, either because it's placed weirdly or we're doing something else that is wrong. So we've sort of exhausted all information that we could get out of the vertex shader stage. So the next stage in this pipeline, we have, you know, these are tessellation stages and then geometry. None of these are enabled right now. We're on the more simplified vertex shading pipeline. So we actually skip directly from vertex shader to the rasterizer, which is the next stage that is actually used here. So we'll go look at that. And see if there's anything here that is relevant. So it doesn't seem like there is. The only thing here that I could see that actually affect things really is cull mode. And we are, if we go in here and check, you know, backface cull, well, there's we're not seeing any indication that we're actually backface culling anything. If we were, this would highlight some portion of the screen to show what triangles are being backface culled. So that's not the solution. So we have our viewports, which just tell us, what the depth range is that we are allowed to be in, what area of the region we render to. These all look correct. So again, no smoking gun there. Pixel shader, I don't expect to be a problem because, well, it does basically nothing. It just copies a color out and puts it. So this is not going to be a problem, I assume. It would confuse me a lot if this was our problem. So that's good. We will have plenty of opportunities later on for pixel shaders to be a problem. They are not here. The only other thing I can think of is the output merger, which, it's what controls output to the render targets. So maybe there's something wrong here. So we don't have a depth buffer. We just have the swap chain image that we found. Which all looks reasonable. We have one blend mode, like one blend output. The actual output blend is disabled, so we don't actually care about any of these values here. We don't have a logic map turned on, and our right mask turns all 4 channels on, so we should be good here. We don't have a stencil buffer. We don't have a depth buffer. And yeah, our blend is turned off, so none of this should matter. So I don't think that the problem is blending either. So what next? Now, the next thing we can look at is this mesh viewer. So RenderDoc actually captures the outputs from the vertex shading stages. So it can show you what the mesh looked like before vertex shading, just by using if you are going through the input assembler, which we are not. It can show you, it would show you here, like, here's what the mesh looks like just from the vertex buffer. Then there's the VS out one, which is, here's your post-projected mesh. Here's what it looks like. So this looks, a bit wonky, but it's not completely alien. But it does look like this is really close to the near plane. It's not clear if this is in front of or behind the near plane here. So that's a mystery we need to solve. we also have output from geometry shader or domain shader if you've got either of those stages enabled, so you can look at. So if you were doing something with tessellation, you could do something like, okay, here's the output of vertex shading your patch, and then here's the output of tessellating that patch, right? But we're not doing that yet because we will do the easy things before we do the hard things. So now when I'm up here, I can see the actual output of the vertex shader. It's just vectors, which is really useful. And if I select a vertex, RenderDoc will actually highlight it on the mesh. So like I can go and see this vertex, or try to at least. It seems to be very far away. So that's not fantastic. So some rather obvious concerns. One is I don't think that any of these end up in frustum after the divide. So we can check this. So we have, let's take this y value, 59.80748, and we will divide by 4.66221. It's actually negative, but so that ends up being like -12. Okay, well, your clip space is -1 to 1, so this is way outside the frustum. It seems like most things in here are, but not all of them. So here, for example, we have 59.80748 divided by 24.64. Okay, that's still outside of frustum. So that's very much a problem, which is that pretty much all of these seem to be, outside of the viewing frustum. Which, is kind of understandable. Because I assume that because we don't have a camera matrix as part of her projection, well, the camera is at the origin. And because we don't have a model matrix, the model is also at the origin. And so if we scroll down here, we can find some cases where these vertices should be on screen. But it's not actually clear whether they are. They don't seem to be. Interesting. That actually is really interesting because, like, this should be C is larger than the rest of the component, or W is larger than the rest of the components here. So this should be on screen. Except wait. When we do this divide, we're going to get a negative Z value out. And our clip space near plane is 0. So that's obviously wrong. Actually, that's not true. Our clip space near plane is actually 1. Our far plane is 0, but it doesn't matter. The 0 to 1 range is the valid range of clip space. Z So that's really interesting. I'm not sure how this is supposed to work. Maybe near plane is supposed to be negative. Let's give that a try at least. I know it's terrible. I'm flipping signs to see flipping signs until things work, but welcome to graphics programming. Picture. Okay, so we have negative. You know the signs are going to cancel, so let's just not bother with this. So 0.1 over 26.62953 is, you know, it's not a very high value, but, you know, that's sort of what we expect. And like, this is fine. This is, most of our values are going to be very small because we intentionally made them very small. Like the entire point of doing reverse Z and extending your far plane to infinity is to sort of bunch up your depth values on small floats, which have relatively higher precision. So actually, I take that back. This is kind of unexpected, because something close to, like, in clip space with reverse Z, or near plane is at 1, not 0. Because you flip the depth buffer around. Which means that this is incorrect, because we shouldn't have anything this close to 0. We should be seeing something close to 1 here, because this mesh is fairly close to the origin. Like, if our units are centimeters, this thing is like within a meter of the origin, which is not very far. So that's very interesting. I feel like I may have my matrix wrong. No, this looks correct. Maybe we actually need a left-handed matrix here. I don't know why we would, but no, that also fails. Okay, so another thing we can try is try moving the position away from the origin. So we'll move it like 10 meters away. Actually, that might be a bit excessive. Move it 1 meter away. Then then we will actually crash. What are you unhappy about? Right, go to here. Why are there no characters? Right. Post, not local position. All right. I don't know why it's complaining about no characters in the input string. Who knows? But it still doesn't fix it. Oh. Oh. I think I found our bug. I don't know how we caused it, but I think I found it. All right. So let's look at these vertex positions. Okay. So like the first three is the first triangle. So we'll look at those first. We have this one, that's it. Basically 18.7, 59.83, and 104.617, right? Look at the next one. It's 18.92, 59.807, 104.66. Then the next one is 18.92, 59.087, 104.66. So these are the same vertex, which means this triangle is not a triangle. It is a line. And if we look at the next triangle, we end up doing the same thing, where it's just, okay, we have same vertex twice in a row here. Then we have a unique vertex, and then we have the same vertex twice in a row, same vertex twice in a row, same vertex twice in a row, so on. So we have a bug in our mesh loading, is my assumption. Because what is happening is we are duplicating, like every other vertex, and as a result, all of our triangles are degenerate, which means they have zero area, or two of the vertices are at the same point. When you do that, the rasterizer sees that, says, hey, your triangle is not ever going to actually cover a sample point because it has no area. Like it can't cover a point because it doesn't cover anything. It's just a line or a point or whatever, right? Like it's not a triangle. Or it's not meaningfully a triangle. It's still technically a triangle because math, but it's a zero area triangle. So the rasterizer sees these and just says, okay, well, this is never going to cover anything, so I don't have to bother rendering it, and throws it out. And because all of our triangles are degenerate, all of them are getting thrown out. So that's clearly a problem. It's not entirely clear why that's happening, but I assume it's happening during mesh loading when we are triangulating our faces. So let's go take a look at that code. So we load out the indices for three vertices on the face. That's face index plus 0 is the first index of the face. Then we take the jth index of the face and j plus 1 index of the face. So that gives us, so if we had, say, a quad as input, first time through this loop we would have 0, we would have like the 0th from the face, the one first from the face, and the second from the face. And then the next time through we would have the 0th, the second, and the third, and then we'd be done with the triangle. So this looks correct. We then use these to fill in our position and normal buffers. And here's the bug. We're using index 1 here when we should be using index 2. the moment of truth. Well, that's disappointing. Okay, I'm pretty sure we're rendering it correctly. We're just putting the mesh in the wrong place now. So we'll get another RenderDoc capture. I really wish that had just worked, because that would have been nice and impressive, but, you know. Okay. So looking through this, like our first triangle here now has 3 distinct vertices, which is good. That's what we want to see. Like some of these are shared components, but that's fine as long as the overall position vector is different between them. So that's positive. Now, I really wish this thing had like a speed control on the mesh thing. So like, if you look real closely, you can see the teapot. There is in fact a teapot there now. We do like solid color shading rather than wireframe. Hey, it's, you know, it's recognizably a teapot, or at least it is on my screen. Who knows what video compression is doing to it. So that's cool. Unfortunately, it is not in Frustum, it seems. It is, in fact, way outside Frustum, somehow. I think. Save this. Yeah, we're still not backface going anything, so. I think the problem is just that it's in the wrong place again. All right. So let's try getting rid of this translation. Hey, look at that. So I think what we were doing here was we were actually moving it behind the camera, whereas this would move it in front of the camera. And there we go. Go ahead. Down like 50 here. All right. We have a teapot. So that's actually really cool. That is not a trivial accomplishment to have to like actually have successfully rendered a mesh without using input assembler, hard mode, So that's pretty cool. All right. So we are going to commit this because why wouldn't we? First, I want to sorry, I was working on the math test stuff before the stream, and I forgot to actually commit it first, so. This is day 5. Oh. What's it? Fixed. Loading was duplicating. Well, okay. All right. Well, what now? So we've still got time. We're only been at this for an hour today. So we're going to do some more work on our mesh loading. So what's wrong with our mesh loading? Well, when you index a mesh, so when you're producing a mesh that goes into draw indexed rather than just a draw, the entire point of the index buffer is that any vertices that you have that are the same vertex, so, you know, the same vertex shared across a bunch of different triangles. You should only ever have one entry in your vertex buffer for that vertex, rather than, okay, you've got this big connected mesh, and maybe a vertex is used 6 times. So if you don't use any indexing, well, you have that vertex duplicated in your buffer 6 times, which that adds up when you have hundreds and hundreds and hundreds of these vertices, shared vertices that get duplicated. So instead, you would have one copy of that vertex, and then you would have multiple copies of the index to that vertex, which, that index is, in our case, 16 bits, so it's 2 bytes rather than the 12 bytes that we spend on a vertex. So if you have a mesh that has a lot of shared vertices, which most models do, having an indexed buffer is, having an indexed model is a big savings to memory. Now, that's not actually the only reason we use them. The other advantage is that the GPU will, so once you do vertex shading, the GPU will cache the output of that stage. And the key for that cache, so how it gets looked up later, is the index, like the index of that vertex. So if the GPU goes to render a triangle that needs vertex 5, for example, and it needs vertex 5, it will ask the cache first. It will say, hey, do you have shading results for vertex number 5? And if the cache says, yeah, I just shaded that earlier, then you don't have to spawn another vertex shader to shade vertex 5 because you already have it. You can just reuse the value out of the cache. Congratulations, there's a bunch of math that you don't need to do. So obviously these caches are not infinite. You will eventually have to reshade vertices if you use them again way after you originally shaded them. There are optimizations you can do to reorder your triangles so that you render things to better use the the index cache. We'll probably do that later. But at the moment, our mesh is created really poorly. Because what we should be doing here is caching the vertices that we are generating, and instead of always adding a new index, we should be trying to look up and see, hey, have we generated this vertex before? Does this vertex already exist? Because if the vertex already exists, we don't have to regenerate, like we don't have to add another vertex to the vertex buffer. We could just index to an existing vertex, which would mean that our vertex buffer would be smaller, and it would also mean that we would get cache reuse from the post-transform cache on the GPU. So, There are a bunch of ways to do this. What I am going to do is I'm going to decide that like when we load the OBJ mesh, the unique data that we have per vertex is this fast OBJ index, which actually has 3 indices in it, or position, normal, and text chord, because OBJ splits its index streams. So if all 3 of these indices are the same between two vertices, then they're going to generate the same vertex. So we can actually deduplicate based on this, which is, like 3 uints, versus having to do like binary comparisons of the entire, well, what are they? They are 32 bytes, I think. Yeah, because 12 plus 12 plus 2 times 4, or like 12 plus 12 plus 8. Yeah, that's 32. So our vertices are 32 bytes. We could do just like a mem compare between our vertices that exist and figure out whether we are generating the same vertex, or we could do a mem compare against like 12 bytes and find out faster. So we're going to deduplicate on this, and then we will go through later and actually generate the vertex buffer. I don't know how much sense that made. Hopefully it made some sense. We'll see. So how do we want to handle this? So this is actually going to go away for now. We'll figure out how to handle that later. Okay, so up front, we don't actually know how big this can be. Because while we know, we can ask the OBJ mesh, how many positions do you have? How many normals do you have? How many text chords do you have? But we can't ask it how many unique vertices it has, because that's like, you can have a vertex of any combination of those. So our upper bound is the total number of output indices, because you can imagine you could create a mesh where every single triangle is unique. In which case, if every triangle is a unique vertex, like if all the vertices in every triangle are unique, then you never get any vertex-free use, and therefore you have the same number of vertices as you do indices. That's the worst possible case. The best case is something like half the index count, I believe. I don't remember. It's been a long time since I've worked through that math, but overall, like we can assume that we will have, like, this is the as much space as we could possibly need to cache the unique vertex indices. So instead of actually outputting these, vertex buffer as we go through the faces, we're going to build a buffer of like unique sets of indices, unique sets of attribute indices. And then at the end, we will have the string of fastOBJ indices that are completely unique, like the entirely unique set of those. And then we can go through afterwards and just sort of one by one convert those into actual vertices. And hopefully there will be fewer of those, so we'll have to do less work and consume less memory of our vertex buffer in the result. Now the trade-off for that is we have to, when we get the face indices, like when we get the attribute indices for the face, we have to go and look these up. Because you don't want to add another entry here if it already exists in this list. So we have to iterate over this buffer for each of these face indices. So that's a bit more expensive, but it will improve the quality of our mesh. It'll make all of the stuff that we do per frame faster, so it's overall going to be a win. In practice, you would do all of this work offline. Like you would do this during a mesh import stage, and you would just generate your highly optimized mesh data, store it in a binary file, load it at runtime, and the user would never actually see any of this. We may get to that point later, like we may get to the point where we have enough mesh data and model and texture data and shader data and so on that we want to bake all of it offline rather than have it all happen at load time. But we're not that far yet, so we're going to do the easy thing for now. So I'm actually going to try to write a function to do this search, because we're going to have to do it 3 times here, and as we've just seen, every time that I just copy and paste something to do the duplication, I end up introducing a bug. So instead of introducing a bug, I'm going to write the code in a function for the search, and then we won't have to deal with copy-paste errors, at least. So first, So we'll say we'll initialize this to -1. So this function will either return the index in this buffer that matches with our new vertex attributes, or it will return -1, which means that you need to add to the list and use the last, and basically you need to add to the list, and that will be the new one. So iterate over the list. One of these days I will learn how to type on this keyboard. If list I equals I don't actually remember if you can just like directly compare structures in C. I don't think you can. We'll do a memcomp. Right. Memcomp returns 0 when the two match, I believe. Right. Let me double check this. And 0 if they all match. Okay. So if they match, then we return I. Otherwise, or well, we set we set the found index to I. Now, these should be unique, so break here. Okay. So this will either give us the index that we need to reference, or it will give us a signal value of -1 that says, hey, we didn't find it, you need to add to the list. So I'm going to call this because it's more correct. Count x0. So if they're less than 0 here, then we didn't find it, so we have to say So we're still doing a little bit of copy paste, but hopefully I will not screw this up quite as badly. Okay, so we now have an index buffer that should be deduplicated, and it references entries into this vertex attributes list. So now we want to now we want to actually allocate the vertex buffer. So this is going to be based on a unique vertex count. Size of DT. We'll iterate over this buffer. So we don't actually need to look at the index buffer for this. We can just iterate over this. This is the unique list of indices now, or the unique list of vertex attributes, if that makes any sense at all. And so we can go through that and write out to the vertex buffer sort of linearly based on that list. And we should have significantly deduplicated the set of things. So let's do that. Okay. Now, this vertex attributes buffer is just an intermediate thing. We don't actually need it in the end. So we can just free this now. So hopefully, assuming I didn't screw anything up, this should render the same mesh and be faster. Or, well, I don't know that it's actually going to be appreciably faster, but it will be better in some abstract sense for right now. Okay, some builds. Does it render? It renders. Fantastic. Let's see. If we get another that capture, yeah, if you look at the input now, so vertex here is just the incrementing index. This is the vertex ID. This is, or well, it's not the vertex ID. This is just like, it's the index into the index buffer, if that makes any sense. So this is just monotonically increasing forever. Whereas the index over here is the index buffer value, which is now no longer just a monotonic increasing thing. It's then we're actually using the index buffer now to duplicate our vertices. So you can see, for example, this first pair of triangles is 0, 1, 2, 0, 2, 3. That's a quad that has been triangulated. So that's pretty cool. And you can see, you know, we're at like vertex 200, but we are only at index in the 40s. Right? So we've significantly reduced the number of vertices in our vertex buffer by actually using our index buffer for something. So our high water mark seems to be like 8,333 indices, or like vertices, but we have, you know, 47,000 indices. So it's like yeah. So our vertex buffer is like 20% of the size it used to be, which is not bad. We got really good results here because this mesh is, like, if you look at the wireframe, it's very much, like, it's very structured. It's actually modeled with Bezier patches for the sides here, which means that, you know, in the modeling package, and actually even in the OBJ file, most of this is just quads. And then when you tessellate quads, you get these vertices that have, you know, basically every vertex on the grid has 6 triangles that use it. Right? 1, 2, 3, 4, 5, 6. And so you get pretty significant savings by indexing a mesh like this. versus something that's like something like foliage, which is just a bunch of cards, often doesn't make a huge difference whether it is actually indexed, because most of the cards are just kind of independent of each other and don't share any vertices. So it kind of doesn't matter as much at that point. Okay. Still do more. So the reason this thing is purple right now is if we look at our pixel shader, it's just outputting color. And our color coming in is just for taking the normal and we're remapping it from -1 to 1 to 0 to 1. So we can have basically, so you can show all the different values of a normal, but keep it in the range that makes for a reasonable color. That makes some sense. So the reason that our teapot is just completely purple is because we don't actually have vertex normals, and so what we're getting is the default normal, which is just straight up positive Z, remapped to be basically 0.5, 0.51, which is sort of a purplish blue color. Now, what we would like is to actually have normals. So in order to let's see. We'd like to have normals, but we don't have them provided by the mesh. Now, we can compute them because there are a lot of ways to compute normals, or at least in theory there are. In practice, when you have just a triangle mesh and you just want some amount of smooth normals for it, the way you do it is you basically average the face normals of all the faces that are connected to a given vertex, and you basically weight them by the area of the triangle that, like each triangle's face normal gets weighted by its area, which sounds really complicated. It actually is not, because the way you compute the normal of a triangle is by taking two edge vectors of the triangle, so I'm subtracting one vertex from the other two vertices in terms of position, and then you take the cross product of those. That gives you the normal direction, and it's also scaled by 2 times the area of that triangle, because that's just how cross products work. So it's actually scaled by like the area of the parallelogram defined by that that pair of edge vectors. However, oh well, that's not really true. In Yeah, it's close enough to true. I think it might actually be the volume of the parallel pipette that describes, but in any case, it's the cross product will give you the correct weighting. So we basically we go through all of our triangles, and then for each triangle we compute its base normal, and then we leave it unnormalized because it's already weighted by the cross product, and we just sum it into each of its vertices, normals, and then at the end we go through and we just normalize all those normals, and that should give us the vertex normals that we expect. So let's give this a shot. So this is not necessarily the best decision. If we can, because the problem that this can introduce is if you have a really narrow triangle, sometimes you can have like two of your edge vectors on the triangle are really long, right? Because you have like a really skinny triangle, and then one of your edge vectors is really short. If you pick the wrong edges, you can run into precision problems with this cross product. So you can do some math check. Okay, given the length of the three edge vectors of the triangle, which two are the correct ones to cross product to get the normal in a stable way? We're not going to bother with that because this mesh is pretty well put together, and we're not aiming for perfection here. So So I believe it is cross A, B, A, C. This might be backwards. We'll see. Then vertex buffer. That's A, that normal. Initialize these to 0, otherwise we'll get weird results. Add the normal to each of the vertices on this triangle. And there we go. All right. So now we need to iterate over vertex buffer. And normalize these vertices, but normalize the normals. That's not what I wanted to do. Please stop that. Okay. Did that work? Okay. So now that we actually have something that is spatially varying, we're seeing another problem, a pretty big problem that we have not done anything about yet, which is this teapot model actually has an inside. Like if you were to fly inside of this teapot, what there is actually a modeled interior edge to it. And also, like, it has a back. And even though we have back-face culling turned on, not all of the back is going to get caught because of that. So what we're seeing here is like the inside bits of it are poking through because we don't have a depth buffer. Like the depth buffer is what says, for an opaque model, hey, I've rendered something that is closer to you. You're not allowed to contribute to the color of this pixel, and that's what gets you your your more realistic, hey, things that are in front of other things occlude those other things, right? You need a depth buffer to do that on a per pixel basis. Well, I mean, you don't need a depth buffer to do that, but it's the efficient way to do it. It's the way the GPUs want you to do it, so that's the way we're going to do it. So because we don't have that, we are seeing the interior bits of the mesh poking through. We have a little bit of time, so I am going to make an attempt at getting a depth buffer set up. We'll time box this to say 30 minutes or so. It's actually Okay. Um, so we're going to need two things. We're going to need a depth stencil view and a depth target. But we should only need one, like a depth texture, but we should only need one of those, I think. So that's beneficial. We should only need one view for depth stencil view, because we're going to use the same depth buffer every frame. This is how we're going to handle all of our render targets, except for the swap chain, is we're just going to have the same render target every frame. So you make exceptions sometimes for like TAA, where you're going to keep a history buffer that survives to the next frame and so on. But in general, while in theory you could overlap two frames by using completely separate sets of render targets, that's not all that useful, and the memory cost of duplicating all of your render targets, especially when you get up to like 4K or larger render targets, like you are spending a whole bunch of memory on something that's not very useful. So you can generally assume that like your frames are actually going to render in order, and as long as you get your barriers correct, like you can just reuse the same depth buffer over and over again between frames, and because your frames happen in order, like you're not going to run into any synchronization issues by using just one depth buffer. So that's what we're going to do. It just has the advantage of like this is this should be not terribly hard. So this is You don't have to worry about the incrementing or anything because there's just one handle because we only have one depth buffer. In practice, you would probably have multiple because you would have you might have multiple views into your scene. So you might have shadows and main camera, and maybe you have, split screen. So you need to render two views into the screen, or you have, you have a security camera that's then rendered into your scene. So you have to have, a camera for it that has a depth buffer so that you get something that looks reasonable, and so on, right? You can end up with multiple depth buffers in the scene, but we don't need those now because we only have one camera view of the scene. So that should do it. We need to actually create the view, which is DX12. To be and we will go with 32-bit floating point. This is important because we did the whole reverse depth buffer and infinite via range. That only really gives you a win if you have a floating point depth buffer. So if you look around on the internet, you will probably find lots of recommendations based on older hardware that recommend like 24-bit integer depth buffer. That's not recommended for most modern cases. I know of at least one exception to that rule, but in general, it's not very useful for a modern engine to use anything but float 32 for depth buffers. I guess the one exception in general is just for memory reasons. It makes sense a lot of times to use 16-bit uniform depth for shadow maps, just because you don't care as much about shadow map depth precision. Obviously, higher precision depth for your shadow maps results in higher quality shadows. So I assume I need other things in here. Let's go. And if I don't need to care about. No. So we do need the actual resource. We'll handle that in a moment. Call this but texture resource. Just makes more sense. See disk and how are we handling this? There. So we will do a similar thing, but different with creating this depth texture resource, because one, we're not creating a buffer here, but creating a texture, which is going to require that we actually handle texture stuff. But also, this doesn't need to be in the upload heap. It's a GPU-only texture, so it can go in it can go in the default heap, which should place it on should put it in GPU only memory. Yeah. So like, this is where your render targets belong. There's basically no reason you would ever want to have a render target in any other portion of memory. The exception is potentially if you wanted to do something like taking a screen taking the screen capture at the end of the frame. Even then, the reasonable thing to do is to have a secondary buffer that you copy into to read back, rather than trying to read the rather than trying to just read directly from the render target. fact, I'm not entirely certain that you can put a render target in here because I'm not sure that you get control over the access barriers for these. So in any case, there's no situation where you want to put a render target anywhere but on the GPU, and that's unless you are doing something very weird, in which case have fun. Let's see. Texture 2D, and then well, 80 by 720. At some point, we need to actually like make this stuff configurable and like handle resize and all of that. But then move up the driver, figure out how this is supposed to be laid out in memory. Care about any of these slides or depth buffer? Yes. Because we have reverse C, our far plane is at 0, so we want to clear our depth to 0. We don't actually care about the stencil side of things because we don't have any stencil. So So we will set this clear value here. So the reason we provide this at initialization time is for hardware-dependent reasons. Sometimes render targets are often stored with some kind of compression in the actual GPU memory when they're in depth target format. Like when they're being rendered to, they're stored compressed. One of the things that makes that really useful is that you can clear a render target that is compressed really quickly by just knowing upfront what your clear value was, and then going through the metadata rather than the actual texture and marking each tile of the texture as actually this tile is clear. Because then you don't have to go and like actually set clear value on the buffer in that tile, because when it goes to access that tile, it's going to say, oh, this tile has been cleared, and like ignore whatever values exist in there and just assume that they have the clear value. And then obviously when you render something to that, it will actually go through and zero out things before it renders into it. But so like there's a little bit of overhead of that management when you actually touch a tile, but for the most part, it doesn't matter. But in order to know what that value is for a cleared tile, you need to tell it up front. Sometimes it's not part of the texture metadata what this is, it's just the driver remembers what the last clear value was on this target. But generally, if you want to get a fast clear, you have to tell it up front, hey, here's the clear value we're going to use. Because these get registered into a table somewhere. So that should give us a depth buffer. Let's actually run and make sure that this doesn't just crash, because it crashes, and that's useful to know. Is that sufficient? Yeah, okay. We have a clear value registered. Now, when we create the RPSO, we need to set depth stencil state. I think we also have to set the depth stencil view format here somewhere, but I don't know exactly where that is right now. So depth enable equals true. Depth light mask. Mask all. Blank. We will use greater than or equal because larger values are closer in our setup. Is there anything else in here we need to set? That is for stencil. That's for stencil. That's for stencil. That's for stencil. And that's for stencil. So since we don't use stencil, we don't care about all that. Yeah, BSV format. XGI format. 32 float. Okay. Where we do set render targets, we need to do so this is also OM. Well, no, actually, it's the same thing. Yeah. So we have that's roughly the descriptor. Pointer reasons. Not sure why it wants a pointer, but sure. So we also need to barrier the like we need a transition for the depth stencil view as well. So we will do that. Assume things are created in the common state, but I'm not sure. After This seems wrong. Okay. I was going to say, because like when you're rendering to a desktop, you kind of need both read and write access to it. All right. Moment of truth. No joy. Every time. Using it when tests will be written by a draw call or clear command is invalid. What? Okay. this is a really bad bit of API because, like, depth test needs both read and write access to depth. Like, there's no way to do. If you have a draw call that has depth test enabled and is writing depth, then like they have to be like, it has to read the depth buffer to do the depth test, and it has to write to the depth buffer to write its depth. So like there's no way to. This should really be resource state depth read write rather than just depth write, because you have read access here. You have to have read access here, or otherwise none of this works. That's just really obnoxious. Okay. So, interestingly, that doesn't seem to be working. I know I sort of hit my time limit that I had said, but we can spend a few more minutes looking at this. So we can RenderDoc again. This is the sort of thing it's good at. Let's put a bit buffer. That's interesting. I wonder if we have the color mode set incorrectly. Let's try none just a second. Yeah, that gives us the right thing. Okay, so we actually have like our triangles are actually wound counterclockwise. There's two ways to get around a triangle. You can go clockwise around the vertices or counterclockwise around the vertices, and that looked completely backwards in the video, I'm pretty sure. Basically, depending on the winding order, your cross product will be positive or negative on one of the faces. Well, one of the faces will be negative. We'll have a negative cross product when it's been projected. And so different APIs have different dimensions about which direction, like which winding order should be correct. I'm pretty sure most APIs default to counterclockwise, but DX12 defaults to clockwise. It's like the right-handed, left-handed thing. Like, it's just different APIs will make different decisions, and you get to deal with the consequences of those decisions. So I think our thing is actually set up with counterclockwise triangles, so we're going to just set that in the pipeline state because that gives us the correct result. Which also tells us that our normal map seems to be correct because the camera is looking along negative z, so positive z should be towards the camera, and it looks like it is here. So I think we got our math correct with the cross products on computing vertex normals and all of that jazz. So that's cool. Look like we have this is wrong. Right, we tell it what state it's supposed to be in when we create it. So, okay. So what was happening there was we were creating the depth buffer texture in a resource state that didn't make sense for depth buffer, and then we weren't acknowledging that when we did the transition to depth right. So the debug layer was warning that, hey, you're doing this wrong. So, that's pretty much all I wanted to do today, but let's try one more thing. It's actually so output in the normal color is, you know, mildly interesting, but let's try like actually doing some incredibly basic lighting here. So we will have a light direction, which I will arbitrarily say is arbitrarily say it's that. And so we will get n.l, which is the dot product of light and input normal. Then we can get a so the sorry, I'm mathing and talking at the same time, which is never a good idea. So the typical diffuse BRDF used, so BRDFs are just like reflection functions. They just find as light comes in and hits the surface based on the light direction, the view direction, the normal of the vector, the other surface properties like albedo and roughness and whatever, like what light actually gets reflected back towards the viewer. So the most common diffuse BRDF is Lambert, which is not exactly a flexible thing. Like, it doesn't account for, is the surface rough or smooth, or, there's all sorts of details about like interreflections between microscopic pieces of the surface that don't get accounted for in Lambert, but it looks close and it's really easy. So Lambert is just n dot L, which is the dot product between the normal vector and the light direction, times 1 over pi, which is just a normalization over the hemisphere. You can get rid of this and then just pretend that your lights are pi times brighter than they should be, but the correct math is 1 over pi times n dot L. And then you scale that by albedo. This is actually technically albedo over pi. So let's just say the albedo. And we'll make this a nice a nice purple color. I have no idea if that's a nice purple color. We'll see. So albedo divided by pi times n dot L. And then all of this times the light color. Which for now I'm just going to say that this light is just white. And then we will output that. This is not actually correct because we're outputting directly to the swap chain. We should be doing like this is a linear value, and we need to rather than talk about it, let's just like actually handle this. So your final output is we will get into this more later, but your lighting values give you a linear intensity of light. they also tend to give you a intensity of light that goes beyond 0 to 1, which is a problem here, but we're going to ignore that particular problem. The output that you send to the screen is not a linear value, because when you are when you are looking at let me try this again. Humans have a variable amount of, we perceive differences in value differently based on intensity, right? So really bright colors, we have a harder time differentiating between two bright values. Is it bright values that get compressed or dark values? Yeah, we have a harder time differentiating bright values. So before we store our color into a low precision target, which is what we're going to give to the screen, we apply a curve to it. So this is not actually the correct curve. There's a documented curve that is a little more complicated than this. It's actually a piecewise thing that's close to this curve, but not exactly. The reason we apply this is that it gives us more precision for dark colors than it does for light colors, because humans are good at telling the difference between two relatively dark colors and not very good at telling the difference between two relatively bright colors, I think. I might have that backwards. I believe it's the dark colors that get more precision, but I'm not braining correctly right now. So we apply this curve on the way out, and then the screen gets this target and it undoes this curve before it puts it on screen. So it's not that we're applying this curve because we think it's perceptually better when we do. It's that this gives us, it redistributes the limited number of bits that we are outputting to handle our dark colors better, because otherwise you get really noticeable banding in the darker portions of the screen. Now, why are we doing it here? Because the output is always going to expect you to have done this. So if you haven't done it, then it's going to undo this curve you never applied, and you'll get a different result than you expect. And when it comes to actually lighting things, that can give you some really weird colors, or it can give you some really weird results. So like your light fall off won't look correct even if it is. I believe that even though we are outputting a unorm target, it's going to be interpreted as though it will have this curve applied because of this, we're outputting directly to the swap chain. So this should give us, well, maybe it'll give us something. or maybe it'll just fail. Right, put this in here. Right, I never defined pi. Let's just deal with definition from here. Um, okay, yeah, it's just something like it's not bright enough. Okay. Maybe this isn't necessary. Oh, because I have this wrong. It's 1 over 2.2. Yeah, there we go. Okay. So yeah, we have a purple teapot, and we even have some basic shading. So that's cool. I think I'm going to leave it here for today. We'll be back next weekend. And yeah, I'm not actually sure what we're going to do. We will find something fun to do. We are starting to get to the really interesting bits of stuff. So we may start refactoring all of our rendering code so that we can, actually set up like multiple render passes and do something more akin to actual production level shading. Obviously, we're not going to get there in one weekend, but we will get started on that. So yeah, thank you for watching, and I will see you next week.